recording. Now, if you've got a notepad, this would be a good time to pull out the notepad. We don't have too much mathematics in this today, but we've got a little bit of maths, and there's maybe a lot of things you want to write down so you can help you do the maths later on. And I don't have my usual clicker thing. Why should we use more timber in construction? It's an open question. Why am I so excited about timber? Why is all my work and all my research all about sustainability in timber?
It's renewable.
It's renewable. It's renewable, yeah. It's renewable. It's also a carbon lockup as well, right? Carbon store. We've got multiple papers. That's Scottish Timber Building. We've got multiple papers that we talk about carbon sequestration, carbon lockup. We'll touch more on that later on. So global warming, right? Let's not be daft. You're probably more up to date on this than I am, so I'm not going to try and patronise you. Global warming is real. There's a nice graph that I pulled out last year, so it's maybe a year out of date now. I find that quite worrying. It's genuine, but that's actually from actual records. Yeah, we'll stop it there. So, I do have notes on this. Is anyone from West Lothian? Where about? Livingston. Alright, so I'll be careful what I say then. This is a town that I grew up in, not in this area. This is a place called Bathgate. Right. I'm not going to ask you your age to try and embarrass myself, really. But this is a while ago. I'm guessing you're what, 20s roughly? Yeah. This is maybe before you were born. Actually, registration plates might help. Right. Anyway, you know the Tesco's in Bathgate? And the houses next door? There, down the bottom end of it. Right. This is also Bathgate area as well. It's a different part, but the same sort of area. And it's a different flood as well. And it flooded for a different reason. I'm not going to the why it flooded because that's not relevant. This one, where's this one? I do have notes. Oh, sorry, it's there. That's just in France. I say just in France. Max Garcia gave me that. One of her former students gave me this photo actually. And you can also have a look at London as well. London tends to build houses on floodplains that they shouldn't be building houses on. So then put measures and barriers in place, which then end up moving that flood problem elsewhere, don't they? I think, who was I talking to recently about this? Amsterdam, right. In Amsterdam, anyone been to Amsterdam before? Napier used to do a trip there once a year with Mark Taylor, and it was an absolutely amazing trip. And here we get taught by him, ask him, is he still doing it? He's not doing it. He did, he did it last year.
I know, we went. That's what we went.
He did, yeah. So they're quite on board with their water management, aren't they?
Right, probably.
That's probably all they talked about.
Oh, I've been.
You were there.
No, but the Champions League was on, and we have not the best.
Right, okay. In Amsterdam, water management's a big thing. In London, it is a big thing, but they don't do it as well as Amsterdam do. But they pay a hell of a lot more tax in Amsterdam just because of that water management. Again, this is a very old photo now. But you can see the comparison, 1941, 2004, glaciers. That's quite worrying. I've got a friend who gave a lecture for me 2 years ago, not in this module, but a different module. And he opened up his lectures from India. He's from, I'm sorry, I forget. It's not Hildwani. It's somewhere down south, right? And he opened up the lecture saying that he himself was a water migrant. Now, I didn't know that, but to be a water migrant, his family had to move because of the lack of water of where they grew up. Quite weird. And after he said that, he had the audience, the class in his palm in his hand, pretty much. He could say anything. They were just listening to him. But utterly bizarre. But it's genuine, and we're going to find more and more. I know this is an old photo. You've probably seen these photos before. They're quite famous. But we're going to find more and more now. We're going to see more famines, more hunger, more problems due to water, due to the fact water is going to become more and more scarce. If people are living from glacial water, there we are. More than 1/6 of the world's population rely on glacier snowpack for their water supply. That's 2005. So I should maybe update that, get some more info on that more for next year. Right. Again, these slides are a bit babyish, but they explain the situation quite well, and we'll try and move on to the more complicated stuff. But we'll just go over the basics. Right, global warming, it's caused by man. Let's not kid on. CO2 in the atmosphere. I do teach a class, not with this module, we go into much more detail and much more depth than just that. And we talk about the different, not just CO2, but methane as well, and what the effects are, and what the half-life of these are. Come on, work for me. Why are you not working? Right. I literally stole this off a children's educational site. Literally, but it's actually lovely. Now, obviously sunlight, photosynthesis, CO2 cycle, and this is the carbon cycle. Right, you've been taught this in primary school, I'm sure you have, so I don't go too much into it. But essentially wood will take carbon out of the oxygen, out of the air, and lock it up into timber. So hence why I tend to like wood. Let me go on a tangent. I've got loads of time, I can do a tangent. As much as I love building real buildings out of timber, and I'll probably hire one or two people in this class over the summer to do exactly that. Well, that's my intent anyway. I've got 2 places up for grabs. As much as I love timber and we build real buildings out of timber, I'm not pretending that building things out of timber is the answer to global warming, because it's absolutely not. Right. The only thing that does is slows down the effects. We still have to solve the actual problem. So I'm not trying to pretend that this is the thing that we're doing to solve the environment. Right. So let's go on to what we want to talk about. There are 2 categories of CO2 emissions. Now I'm focusing on CO2 for this lecture. It's nice and easy for me. Carbon dioxide due to building operation, heating, cooling, just the running of the building. The embodied carbon of, give me 1 second. Clear my throat. I might have some water with me, but as I said, I ran late this morning. Right, we've got operational cost of the building, right? Then we've got the embodied part, i.e. what it takes to make the building. Now, again, we'll go off topic. Anybody watch Jeremy Clarkson's
Farm?
No, not Farm. Farm's good though. But see the Grand Tour or Top Gear?
Yeah.
Right. Show my age now, but Jeremy Clarkson said something a long time ago. He's not known to be an environmentalist because he's not known for that. However, he makes some good points. He talked about cars, and he was asked a question about what car is best for the environment, and he said, actually, the one you've got right now is the best one for the environment. You keep that car for as long as possible. You don't trade it in. You keep it. But if it gets damaged, you repair it, and you keep it for as long as possible. And this is what he then said, and it's backed up by actual science. So it wasn't him that made the science; he just reported on it. The embodied carbon in a normal diesel or petrol car is about 50% of its entire lifespan. is made before the car's even done 1 mile on the road, or 1 kilometre on the road. Then, so if you can keep that car for say 20 years or more even, then you're doing better doing that than you would be buying a Tesla or buying an electric car every 4 years. Okay? Now, why would they go on that rant for? Yeah. So it gets very weird to think of the operational use of the car as only 50% of its overall life expectancy of carbon, which is bizarre. People think, how is that possible? But the people have calculated that, and that's what they reckon. Now, with electric cars, it's even worse. The operational cost comes right down, but the embodied carbon, to make that gets more pronounced. I'll be mindful of what I just said there, though. I'm not saying buying electric cars is bad. I never said that. I just said the embodied part of an electric vehicle is bad, but the operational side of an electric vehicle is significantly better. Overall, an electric vehicle should be better than a diesel car, or is better, not should be. Right. So, let's put this back into a building's point of view. What is the embodied carbon in a building, you think? Yeah. So if we talk about embodied carbon of a building, say, is it 50% of its overall life expectancy of carbon, or would it be a lot less? So people have been doing research on that. Now again, the obvious answer would be, well, what building is it? What are you building it out of? Building it steel, concrete, timber, and you building it as a big, massive structure or a small house. It all depends. All depends on one thing called an aspect ratio of floor area to walls and roof area. Right. So let's try to get back into this for a second. When we calculate the overall life expectancy, the overall life cycle emissions of a building, we need to include the operational and the embodied. And I would also argue the end of life as well. Right. Again, I'm going to go back to my simplistic slides. This is the embodied CO2 for some common construction material. Steel is 1,444 kilograms per ton of steel of CO2 equivalent released into the air just by making that steel. Actually not too bad, you would think. Concrete is only 210 kilograms per ton of concrete of carbon that's released into the air. Right. And timber, this is a shocker. Right. Timber is actually, looking at this, horrendous. Right. The reason why this number looks horrendous, you may want to talk about this in your stuff, is when we plant a tree, say a tree takes 50 years to mature, you plant it, you have to manage that area for 50 years, and once you've managed it all, you then start felling the trees down, and you process that timber or that log into timber. All of that effort takes carbon, it takes the energy to do all that. Hence why it's carbon expensive. Timber is carbon expensive to produce. However, timber sequesters carbon. Timber will sequester carbon. I do have slides. I looked at these slides last night before I came, and I thought, I don't want to paint the wrong picture. Normally I'll go from this slide here into some lovely slides where I'll talk about sequestering of carbon, and it makes timber look amazing. But I thought, no, we need to be truthful here. So let's talk a bit more truthful about the end of life. So we build a building out of CLT or something, and that building lasts, say, 200 years, and at the end of it, we just bulldoze it and let it rot. What happens at that point, end of life? Because if we don't take that into account, then we're doing ourselves a disservice, or we're telling lies. Right. So timber turnover timescale, TTT. Sorry for the bad joke, but it's a logarithmic timescale. It's not my joke. Right. This means newspapers. Sorry, I do apologise. If you print paper, like newspaper, you read it one day, tomorrow it's old, so it goes in the trash. It'll take a year for that newspaper to decompose in the landfill site. If it's flat pack, well, what flat pack there is referring to is your IKEA furniture. Now, I'm not saying that IKEA furniture only lasts 10 years. It's not what I said. But the IKEA furniture, once you put it in landfill, now if it actually goes to landfill and it doesn't go to biomass or it doesn't go somewhere else, goes to landfill, it'll degrade in 10 years. Now, I'm referring to chipboard, MDF. I'm not referring to solid wood. Right, so flat pack furniture, your IKEA, some of your IKEA type stuff. Buildings. Right, sorry, I am actually. Sorry, I do apologise. Take 2 seconds back. I'm referring to the furniture here. So the furniture average lifespan approximately 10 years. For IKEA, that's about right. For normal buildings, average, like a house, 100 years. For a cathedral, average life, 1,000 years. Some a lot more. Well, some are a little bit more, sorry. Anaerobic storage, i.e. without any oxygen. So if you get a piece of wood and you dump it into a bog, a peat bog, right? You ever heard of bog oak before? I'm gonna have to buy some. I'll have to buy some. It's quite expensive, right? So if you can actually buy bog oak for making things out of. It's usually quite small. You won't get very big bits of it. It's essentially a tree, usually oak trees that have been growing and that has then just been submerged into a bog, and it's been there for 10,000 years plus, type of thing. And furniture makers, buy this bog oak, and they make it into wonderful things. I'll have to try and buy a small piece. But they reckon that the storage of carbon in there will last about 10,000 years before it's released back into the environment. Fossil fuel is millions of years, to be brutal about it, or 100 million years, to be brutal about it, before it's turned into fossil fuel and then actually eventually then burnt back into the environment. Right, okay. All very good. Right. End of life options for wood. Right. So you build a building, you use GLT beams or CLT beams. At the end of the building's life, you could reuse or repurpose that timber and put it back into a new building. No problem. Pretty sure. Or you could recycle it, make it into pellets or something. And you could offset that against part of the project. Now, there will be some leakages from that. So some of that material end up going to landfill, a small percentage, but you can recycle the product, essentially. Energy recovery, we talked about biomass. No, we haven't actually, but you could put it into biomass. When you put it into biomass, some of that's offset. Offset how? Well, you're generating power, you're generating electricity or heat or whatever it is you're generating. But then that releases CO2 into the atmosphere. So that's problematic, potentially. And then landfill, if you put biogenic material, anything, food waste, anything at all in the landfill, you will be creating LFGs, i.e. methane. You'll create methane in there and it'll be released either into the atmosphere, which you don't want to do, or you could in fact capture that methane and use that as natural gas, believe it or not. So either methane captured for reuse or methane emissions to the atmosphere. And there's also going to be leakage from that system as well. Right, that's where the notepad comes out. You write these things down, please. So the relative mass of carbon, now you remember from your chemistry at high school? What unit is that in again? The periodic scale. Sorry? I'm actually definitely. It's not you, it's not your voice, it's actually me. One more time. EMU, atomic mass. Thank you. The atomic mass, EMU. Right. So carbon is 12, hydrogen 1, oxygen 16. Oxygen's heavy, yeah? So carbon dioxide, CO2, 1 carbon, 2 oxygens. So that'll be 12 plus 2 times 16. So carbon dioxide is 44 atomic mass. Methane is CH4. C is 12 plus 4, well, plus 4 times 1, sorry, 16. So that's methane. GWP just means global warming potential. It's written there actually. Global warming potential over a defined time horizon of giving a mass of gas with respect to the same mass of CO2. So global warming potential of CO2 is divided by exactly 1. Methane has a stronger global warming potential effect, but has a much shorter lifespan or lifetime in the atmosphere. So GWP 100. Now, when we write GWP, we're actually meaning is it over a 100-year period? That's what we actually mean. We don't write GWP brackets 100 close brackets, but in actual fact, that's what we're meant to be doing. But we just assume that it is. However, yeah. So with this statement here, the global warming potential effect. Sorry, I'm being dumb for a second. We'll look at it like this. So methane has a stronger global warming effect, but shorter lifetime in the atmosphere. That should be a new line. Okay. So the numbers in bold green, we'll be reusing them later on further slides without any further explanation. So please, have you written the numbers down, yeah, and what you mean? Cool. Right, able to move slide yet? So I'll go back if we need to. Is it? No, we'll go one at a time. Right, an example calculation using a GWP of 100 as a basis of evaluation. What is the advantage of flaring, i.e. burning gas out of these tall chimneys? Now, Livingston, you got a clear view of Grangemouth, right? And you see Grangemouth in the evening sky. It looks like Aurora Borealis, but it's not. It's just actually flaring, and it's bloody loud, isn't it?
I know.
It's really loud. Napier's got a contract to monitor their volume. So we send people out there on a weekly basis just to monitor their flaring. It's a legal requirement. They spent something like £28 million on a new collar just to reduce the level of sound and the flaring. Just to bring decibels down. Anyway. And then they're threatening to shut the place. Bit bonkers. Right. Yeah. So the baseline, as it has a GWP of 28. Hold on one second. What am I doing here? Am I being dumb? I think I might be. I got my pointer. My pointer not here. So I've got everything else other than the things that I want. Right, sorry. Well, actually, I'm going to say that I'm looking at this myself, to be honest. Been a long week last week. Right. Example calculation using GWP 100 based on evaluation. What is the advantages of flaring? Are you burning 10 tons of methane from a landfill site instead of allowing it to be ventilated into the atmosphere? Right, that's a valid point. So if we release that into the atmosphere, or we flare it, what's the advantage? As a baseline, as it has a GWP of 28 over the 100-year cycle, the 10 tons of methane is 280 tons of CO2 equivalent, right? Assuming all of the methane is converted to carbon dioxide if flared. So that means, that methane, which is carbon and hydrogen, one carbon, 4 hydrogen, plus 2 oxygen. Oh, no. Yeah, methane, right? That's just oxygen. Yeah, that's flaring aspect of that's a flaring context. That then gets converted to this. So assuming all the methane is converted to carbon dioxide and flared, I see. That makes more sense. You're removing the hydrogen from here to here. Yeah, that does make sense. So the mass of the CO2 emitted is 10 times 40 divided by 16, which equals 27.5 tons of CO2 equivalent into the atmosphere. So we're going to compare the baseline of it being released into the environment without flaring of that compared to if you flare it by converting it to carbon dioxide as that. So that then means you're about 90% better to flare it than you are to release it into the environment. Does that make sense? Yep. Cool. It's Monday morning, I know. And it might have been a few years since you studied chemistry as well. So I do apologise for that. This will not be in your exam. This is for edification for you to understand better. So when we see flaring, don't think of it as necessarily a bad thing, because so obviously in this example here, far better to flare it than it is to just release that methane into the air. And that does not give you the right to go to a farm and put a match to a cow's bum. Don't do it again. Right, anyway. What you could do is that you could capture that methane, not just flare it, but you could actually capture it and use it for cooking, heating, yada yada yada. And that's actually quite a well-known practice. Where's the mouse? Come on. So in this case, 27.5 tons of CO2 was going to be emitted anyway. So the improvement is the full. So if we were to capture that to 27.5 tons and use that for heating or doing something useful, then in actual fact, our improvement would be 100% if we were to do that. Right, landfill. Landfill would follow the carbon. Right, again, this might be a little bit high level, to apologise, but here we go. So landfill would, we've got carbon, we've got the bond, which is hydrogen, nitrogen and oxygen, etc. We've got elements of water in there as well. So remember we talked about the water inside the wood, the 10%, 11%. By the time you put it in the landfill, it'll be like more like 50%, to be honest. So if we break that down into, we've got a starting point. Yeah, this is a diagram following the flow rate of 100 grams of carbon in the wood. So ultimately it's 100 grams of carbon. We're not going to follow these, we'll just follow this. We'll put that in the landfill. So obviously it's a total of 224 grams, but the carbon is only 100 of that. 100. Already you've got 10% of that carbon will go straight into methane as it decomposes. Sorry, let me just rephrase that. LFG. That LFG is 10 out of that 100. From that 10, 50% of that, or 5 out of the 10, will become methane straight away. We've got methane capture, methane emissions, or we've got some of that 10 or 5 of it will become CO2 emitted. Right, let's try to put some numbers to that now. Wood products in practice have a moisture content of about 12%. Remember, you converted your numbers to 12% for your, I know you done that, didn't you? You converted your coursework number 1, you converted your mass to 12% moisture content. Of course you did. Yeah. Right. Okay, that's fine. So the timber product with an oven dry weight, i.e. no moisture content, of 200 grams would in practice weigh around that's fine, but we'll understand that. The oven dried part is almost precisely 50% carbon. So therefore, that's where that 100 came from. The wood is a mixture of cellulose, that word there, the lignin. Lignin is like the glue that holds the cells together. Lignin is quite a big part of what we do research in, which are degradable in anaerobic conditions, i.e. without any oxygen, to different degrees. Lignin, not at all. So lignin doesn't degrade, but the others do. A reasonable assumption is that even after a long time frame, only 10% of the wood will have decayed. Landfill gases. So landfill gases is assumed to be a 50-50 mixture of methane and carbon dioxide. 5 grams of carbon goes to each. Yep, fair enough. Approximately 70% of the LFGs is captured, with the rest leaking into the atmosphere. So this is on a modern landfill site where we can actually do capture. Not all landfill sites do carbon capturing. We're not going to go into that in this module. It's very interesting, but it's not for this module. The emissions, therefore, would be 5 grams of carbon in the landfill gases, CO2, is equivalent to 18.33 grams of CO2 equivalent. The 1.5 grams of carbon that is emitted as methane equates to 56 grams of CO2 equivalent. And the 3.5 grams of carbon in the captures within the methane amounts to a zero impact, i.e. it doesn't get into the environment, or 9.6 grams if it was flared. Total emissions therefore is around 74 to 84 grams of CO2 equivalent. I would take your time and go through these slides again. Right, you do want to get your head around this. So we've just talked about, in the previous one, we've talked about it in a landfill situation. Now let's now talk about it in the incineration example. In that incineration example, 100 grams of wood carbon will emit this directly into the environment. If the energy is recovered, say by heating instead of fossil fuel or natural gas, and the emissions is offset. The calorific value, or CV, of wood is approximately 5 kilowatt hours per kilogram of wood. 100 grams of wood carbon is 224 grams of wood. Now, we generally burn our wood below 20%. You'd expect it to be 12%, but I can tell you now, most people that burn wood don't burn it at 12%. They burn it about 18% on average. I know that because I used to do it. I used to heat my house with just wood. Well, I had gas as well, but mostly wood. And you can do the best things you can, store the wood outside and make sure it is below 20%. You can do all of that, but it will never be at 12%. Not unless you have it in the house for months beforehand. Right. I do what my wife's done. She stored all the wood behind the fire, and it then catches fire. Not good. Right, so I get back on track now, right. So the calorific value of wood, approximately 5, blah, 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 blah. 100 grams of wood carbon, it'll actually weigh that, as we already know from the previous slide, will produce 1.1 kilowatt hours of heat. Methane CV is approximately 15 kilowatt hours per kilogram. So let me get my head around that. Yeah. So methane is actually better. Quality of methane needed to produce 1.1 is this with the problem. So taking an offset into account, the emissions is going to be that. So what's my question though? Can you not understand what I've done there? Would it be better for me to get a piece of wood and burn that wood to heat my house or say lots of wood to heat my house? Or would it be better to take that piece of wood and put it to an anaerobic or an oxygen filled environment, capture the methane, and use the methane to heat my house? The answer is here. Yeah. Sorry. Going too fast. Right, there we are. Yeah. So this is approximate 200 kilograms of CO2 when burnt. So in actual fact, that 367, where does the 367 come from? That comes from the previous one, yeah? 367. I'm just being blind. There we are. So if we just take the wood and burn it, that's what's released into the environment. But if we shake it into methane and burn that, that's what's released into the environment. So the offset is that. So the answer is actually no. It'd be better to take the methane and use that environmentally. Right, there's a caveat to that blows this all out the water. Right, if you just do the top run and you just burn wood, but you burn it not at 12% content, but at say 20% or higher content, all of this mass goes out the window. Right. Bear in mind, we've already said that making the timber into methane and burning the methane is better for the environment than just burning the wood anyway. But what I'm now saying is, if you then burn the wood when it's slightly damp or too damp, these numbers get even worse. That number will probably double, to be honest. Okay? So the moisture content of the wood has a massive effect. If you turn it into methane, it's actually significantly better. Right. I'm doing a very big disservice to timber at the moment. I'm pretty much saying timber's bad, but I'm not. I'm not saying that. But how we manage our timber and how we recycle our timber is very important. Right, this is a photograph of OSB. What do we know about OSB? One of our biggest exports in Scotland. An awful lot of jobs are created from this. So Stirling board manufactured this with Stirling and the north east coast of Scotland as well. Apart from oil, salmon, meat, probably whisky as well, OSB comes after them when it comes to exports financially. So it's a massive export for Scotland. Pretty good thing. And you've all seen the OSB before, yeah? Cool, right. It's not a simple board, it's quite a complex structure and it's doing quite a lot of things. Essentially, the end of wood recycling, rather than turning it into biomass or into methane to burn, we could just chip it and make it into very high value products. Right, we'll try something slightly different now. As a matter of fact, using timber and construction material helps tackling global warming. There are other advantages in using timber-based materials in construction. Timber structures are lighter. When we talk about timber structure, timber versus steel or concrete, the strength to weight ratio, timber wins every time. I will caveat that and say it's strength to weight ratio. You will get a smaller size beam made out of metal than you will do out of timber, but if it's strength to weight ratio, timber is better. So just be very mindful of what I'm saying there. Timber construction is usually faster safer than metal or concrete construction. That's a very broad statement I made there. Why is my mouse not working? Right, we're coming to the end of these slides. Right, this is where we normally go with this class. I wouldn't give them all that extra detail. I know you might be a bit bored here, but I hope that was helpful. Hopefully you took in some of that. Now, this is the sort of thing. Let me just turn this off. Guten Tag. I'm trying to sell a house. I thought it might have been, but it's not. Right. This is a project that I got a student to do from a number of years back now. His name was Victor Henkel. We actually built 15 of these in real life. And what they are is like small bosses. But he didn't build them, he done the maths on it for me. He was paid to do it. Now, what we essentially done was designed that similar to what you done last year with me. You designed something like this, and then worked out all your volumes of material. You then converted that to GWP with the carbon sequestered in the timber was that. We then compared that to a reduction in miles driven by a standard family car. So simply by building that, we then lock up carbon into the building. Hopefully that building will last longer than the time it took to grow the timber in the first place. That's a reduction of say 14, that's what, a year and a half an average family car. Now we've done the same exercise but for a family home. So 3-bedroom semi-detached. We've done it actually 10 times, not this number here, 4 times. We benchmarked it as a brick and block English style house. That's how they still build in England at the moment. We benchmarked it against that. We then said, right, if we convert just one thing, internal timber back there to timber frame, what would the difference be? This is for just one house. It'd be equivalent of not driving the car for 4 years. One car, I may add. We then changed it from an open panel to a closed panel. That just simply means 2 sheets of OSB, one either side. And most of our new houses these days will be closed panel because of the structural advantages that it gives. It allows the architects and designers to have more freedom with larger openings and bigger windows and doors and things. So they all tend to be that anyway. And you see just by that extra sheet of OSB and the extra things we had to add in, it then meant the reduction between the benchmark was about 8 years worth of not driving one car. If we then done a full closed panel, but then took away the external block work and put a cement render board on, some companies already do this sort of thing. That then meant it was even more, almost 9 years. Right, that all sounds very good. But if you want to build just one house, the equivalent of not driving your car for 9 years, fair enough. We have to build 200,000 houses each year. That's what we need to build in the UK alone just to meet our current targets. If we can change, now most of those are built south of the border, not north of the border. And currently at the moment, a lot of them are built like that. If we can change them to build more like this, you'll get better U values for a start, you get better other things, but you'll also have a much more reduced carbon footprint. And we can change how we construct things going forward. This is probably my last slide. What did I add there? Oh, all I added was that little symbol. Fair enough. Right. So that's for the timber aspect of it. Next week we'll be looking at timber part 2 next week. So for the rest of the day, what have we got on the rest of the day? We have got, I'll be brutal with you. Has anyone been downstairs last week? Down the heavy structures? Anyone seen the? Yeah. Have you?
Yeah.
Quite smart, yeah? But none of you know what I'm talking about. Right. I'm hoping you're allowed to go in there today. Hold on, let's see. Now, right. So, I'll give you some options then. For the people that are here just now, how did you get on with doing the graphs in Excel? Oh, pretty easy, yeah? Right. I know I was talking to one student. Where is this? And there might have been a small misunderstanding. Let's talk about. Oh, have I given you your checking code yet? Oh, not yet. I thought I had. Sorry. I apologise. Anyway, I'll finish off my sentence first of all. We need, for here, I'm going to keep that time slot as it is. The reason being, I've not checked with Gary if he's even able to take us early at all. And if he's not even ready for me, I'll have to go and make the samples for that. I hope he is. But if you were down in the lab last week?
Yeah, last Thursday.
Last Thursday, right? Is our machine still there? Or has it been moved?
No, it was still there when me and Sean went down on Thursday.
Last week?
Oh, maybe both of them.
No, there's a big structure there now.
There was a wooden set in the corner when we went to look at the dry mass.
All right. So what you've now got a grid shell. I'm going to find you a photo of it. So they've got this grid shell downstairs. And I'm hoping we can still get in. That was a fourth year student that made that. Right. The only difference really in the first coursework and the second coursework is this. I do have. What do you want to do? Do you want to take a 20-minute break and we'll go up to E32 and we'll go over for half an hour what you're meant to do for the second coursework? Do you want to do that? I can give you last year's data and we can process last year's data, and obviously you'll have to then do it from scratch once we get today's data, once we get it from Gary. Do you want to do that? Right. If then you give me a 20-minute, let's meet at say 11:10, right, in E32. That'll give me time to make sure that we're ready to go down in the lab, right, and have the testing done. If I get the opportunity to move this up a little bit, would you want that moved?
Yeah.
You would. I thought you might. But what we also want to make sure, let me just whet your appetite a little bit. Look, I'm still recording. I'm going to stop recording now.